Yes.
50 minutes.
Go. Okay, right. We're Project segtrax, and we're going to try a free-form jazz approach to this, where we'll go in turn. So I'm just going to do a brief introduction on the problem, and then we will each go off and talk about the work that each of us have done as part of this. I should preface this by saying we hope to have a final project or product at the end of this. We don't, but we've got lots of things to show you. So an acute fluffy cat at the end. So the problem that we're trying to solve is that sea ice is in motion, and we want to be able to try and come up with a. There we go. We want to be able to come up with some kind of workflow to deal with ice moving over the Arctic. This is our map of the Arctic. We've imported whiteboard here. So our tasks were to read ISAT2 and extract segments and read those into a trajectory object, and then take those trajectories and move them over the Arctic using ice motion data, and then try and get some reanalysis and use a freezing degree day thickness method to evolve those segments. That was the plan. We've got most of the parts of that built, but need to bring it together, and we're going to continue working on that after this hack week. So I will hand over to Dave.
Okay, so Walt and myself dealt with kind of the first two tasks of this, and we'll preface this again with both of us are brand new to Python. So it was an adaptation of Amy's code, but basically we developed a notebook where you could define a region of the Arctic, select a time period, and set up to download all of the available sea ice data for that region and over that time period. If we go back up to the beautiful map that Walt drew from memory of the Arctic Ocean, we decided to limit our spatial extent to the eastern Arctic and to focus on ice that is entering the transpolar drift stream. We felt that in dealing with this area, we would be dealing with just seasonal ice that we didn't need to contend with snow accumulation on, or we didn't need to contend with it as much. So yeah, at the end of it, we basically had, I think it was about 3.5 million freeborn segments in that region over that time period. And then it got broken up into different objects that these guys then processed through.
Okay, yeah, and I'll just follow up. Yeah, that's my map. And so one of the things that I got out of this is the realization that I chose wisely not going to art school. So maybe you can follow that. And again, yeah, also help at least get going on some Python skills. As we talked about, we used a simple ice growth model. So the idea is that we could take the initial freeboard and then vect it as well, and using reanalysis, atmospheric reanalysis, thicken the ice over time, and using this equation right there at the bottom, and that's from Lebedev, 1938. So I'm going to throw that out there as the oldest reference. See if anyone can beat that. And so I think we've gotten pretty close, but didn't quite finish up. But I think we got some interesting things to show. So.
Yeah, so once Walt and Dave downloaded the data, we needed to extract it and get it in some format that we could use easily. So our first attempt was to create just a regular Python class with different members that we thought would correspond to the different data we were interested in. But after going through some of these tutorials, it became obvious to us that a GeoPandas data frame or an X-ray or something like that is a much better way to do that. So future iterations will implement that instead of just a normal Python class. So once we read in all the data, we iterated over each file and created these different class objects that stores the data, which we can then evolve through time or move around or manipulate. So once it's in that format, we can do some of the calculations.
Yeah. So yeah, I was part of the 3M. Where is our?
I don't think I have your info.
Yeah, I was in charge of the tracking of the sea ice movement using the UMV field from the ice motion. So after getting the ice at coordinates, so we have, in order to track the sea ice, I used the ice motion field from UMV. I haven't experience with the Python, but as Andy explained, that the X-ray is the useful and powerful tool with a bunch of data, use the investigate data, so it was very useful to use it. And to make a new position of the UMV vectors, and I added a new V field to the X field, and I added V field to the Y field, so which makes a new position of the X and Y, and I converted the X and Y field to the unknown using transform. Yeah, it was used, which need EPS data, EPSS numbers, so it was useful as well. So we got some new new position of the ice motion vector use the UMV field. Yeah.
My section was the very last one, number 6, which was getting in ERA interim reanalysis data, and then Walt showed me with this equation how to calculate freezing degree days from 2-meter temperature, and then calculate thickness using this equation. And then so what I really wanted to do was to somehow integrate in reanalysis data, which is what I primarily use, in with the ISAT data. And so what I did was I kind of worked backwards on both ends, and I didn't quite get to the middle to really put the two together, which is what I wanted to do with what Andy showed earlier with the vectorized indexing method. And so that's something that I'm going to do after this. But what I did was I read in the freeboard heights from detail 10, and these are what I'm showing here. And then just like different ways of visualizing these freeboard heights here. And then what I did was I took that thickness equation, and then I went backwards to calculate an initial first I took Alex's freeboard to thickness function to calculate thickness from freeboard. But in this function, I got rid of the snow depth and snow density since I didn't have any of that data to use here. So this is just the thickness based off of freeboard. And so I got the thickness, and then I calculated freezing degree day from that thickness. And then I was going to use this as my initial freezing degree days, and then add it on to the ERA interim calculated freezing degree days to calculate a change in thickness over time. And so here are my, this is kind of where I got stuck, and then I'm going to come together in the middle after this. But here I use that widget interactive plot function here and these are the cumulative thickness change for the sea ice over each week during the 4 months that we looked at. And so it should be changing. Maybe it's very small, but it's supposed to change over time. I might need to run all these different blocks first to get it to run, but here I have this widget, and it'll eventually get up to as high as about 175 centimeters over the course of these 4 months here. And so what we're going to do is use that to calculate the thicknesses on top of the trajectories.
I'll try and wrap up. And yeah, so that's kind of where we are. Lots of parts, not yet kind of mixed together and baked, but hopefully we'll be able to collaborate on that and get to an endpoint. But I think it's kind of a valuable exercise for us, but also might provide some insight into how we can come up with an improved monthly mean thickness field, taking into account that ice moves. So thanks very much. Thanks very much to the organizers. It's been very valuable, certainly for me. I think for everyone else. So